Good morning, student. Today we'll continue with the second half of the topic on time value of money. So these are the content that I will cover today. All annuities or uniform series you have seen last week involve the first cash flow being made at the end of the first period, and they are called ordinary annuities. We also need to be able to handle cash flows that do not occur until some later date. If the cash flows does not begin until some later date, the annuity is known as a deferred annuity. This situation is portrayed in this figure, in which the entire frame of ordinary annuity has been moved away from time present or time zero by J periods. We say that the annuity is deferred by J periods. J is always smaller than N, which is the total number of compounding period. When the annuity is deferred by J period, then the first payment of the first cash flow of the annuity is always defined to begin one period after J, which means at the end of period J plus 1. Finding the value at time 0 of a deferred annuity is a two-step process which involves this formula. First, we can use the uniform series present worth factor to find the value of the deferred annuity at the end of period J, where there are n minus j number of cash flows in the annuity. We can call this as the present value at period J and annotate it as Pj. Now in the next step, we can treat Pj as a future value with respect to time 0. We can change the annotations to Fj and subsequently use the single payment present worth factor to find the equivalent value of the deferred annuity at time 0, which is annotated as P0. Let's take a look at one example. Present equivalent of a deferred annuity. To illustrate the preceding discussions, suppose that a father, on the day his son is born, wishes to determine what lump amount would have to be paid into an account bearing interest of 12% per year to provide withdrawals of $2,000 on each of the son's 80th, 90th, 20th, and 21st birthdays. The problem is illustrated in this cash flow diagram. You should first recognize that an ordinary annuity of 4 withdrawals of $2,000 each is involved, and that the present equivalent of this annuity occurs at the 70th birthday, where uniform series present worth factor for deferred annuity is utilized. In this problem, n is equals to 21, and this is the total number of compounding periods, and j is equals to 17. Okay, this is the number of years the annuity is deferred. Okay, in these equations, we will first find the present equivalent value at year 17 for the annuity from year 18 to 21 using the uniform series present worth factor. Specifically, we multiply the annuity of $2,000 with the factor at the interest rate of 12% and the compounding periods of 4 years. Okay, 4 years here is obtained by n minus j, which is 21 minus 17. Okay, P17 is found to be equals to $6,074.60. Okay, now that P17 is known, the next step is to calculate P0, or the present equivalent value of the annuity at time 0. We will treat this present value as a future value with respect to time 0 and use it to calculate the present equivalent value at time 0 by multiplying it with the single payment present worth factor. Okay, this factor takes the same interest rate of 12% but have a longer compounding period of 17, which means from year 0 to year 17. Okay, this is the period where the annuity has been deferred. You will get $884.46, which is the amount that the father would have to deposit on the day his son is born, in order for him to withdraw $2,000 on each of the son's 80th, 90th, 20th, and 21st birthdays. This is the second example. Deferred future value of an annuity. When you take your first job, you decide to start saving right away for your retirement. You put $5,000 per year into the company's 401k plan, which averages 8% interest per year. 5 years later, you move to another job and start a new 401k plan. You never get around to merging the funds in the two plans. If the first plan continues to earn interest at the rate of 8% per year for 35 years, after you stop making contributions, how much is the account worth? This is the solution. This cash flow diagram clarifies the timing of the cash flows for the original 401k investment plan. This is the ordinary annuity continues for 5 years, involving 5 deposits, each amounting to $5,000. We are required to calculate the future equivalent value of the annuity by the end of year 40. The easiest way to approach this is to first find the future equivalent of the annuity in year 5, which is F5. We can multiply the annuity of $5,000 with the uniform series compound amount factor at 8% interest rate and 5 compounding periods from year 0 to year 5. And we get the future equivalent value of the annuity in year 5 equals to $29,333. In the second step, we can treat F5 as the present value with respect to year 40, where the future equivalent value is to be calculated. And we can change the notations to P5. We can then calculate the future equivalent value at year 40 by multiplying P5, which is $29,333, with the single payment compound amount factor at 8% interest rate. The number of compounding period would be 35 from year 5 to year 40. This gives the total amount of account equals to $433,697 by the end of year 40. Let's take a look at the third example, the present equivalent of BP's payment schedule. Millions of gallons of oil flowing unchecked into the Gulf of Mexico from an undersea well. In response to this tragedy, British Petroleum or BP will make payments into a fund to pay for some of the damages to the Gulf Coast resulting from the massive oil spill in April and following months of 2010. BP will pay $3 billion at the end of the third quarter of 2010 and another $2 billion in the fourth quarter of 2010. 12 additional payments of $1.25 billion each quarter thereafter will result in a total of $20 billion having been paid into the fund. The interest rate is 3% per quarter. What is the present equivalent value of BP's proposed payment schedule? This is the cash flow diagram which we can draw for this problem from the viewpoint of VP. We use end of quarter to represent the interest period. By the end of the first quarter, there is a cash outflow of $3 billion. By the end of the second quarter, there is another cash outflow amounting to $2 billion. Subsequently, there is an annuity payment of $1.25 billion for 12 years, from the end of quarter 3 to quarter 14. Altogether, BP has paid $20 billion. The task here is to calculate the present equivalent values of these $20 billion which were paid at different time points, considering the 3% compounding interest rate that the money can earn. For the cash flows in the diagram, we can formulate a composite equation like this to calculate the present equivalent value of these $20 billion. Here we shift the $3 billion from end of quarter 1 to time 0 with the single payment compound amount factor at 3% interest rate and 1 interest period. We use the same formula to shift the $2 billion from the end of quarter 2 to time 0, except that the interest period is replaced with 2, which corresponds to the 2 interest period between time 0 and end of quarter 2. For the deferred annuity, we can combine the uniform series compound amount factor and single payment compound amount factor to shift these annuities to time 0. Specifically, we can multiply $1.25 billion with the uniform series compound amount factor to find the present equivalent values of the annuity at the end of quarter 2, or P2. And for this factor, we use 3% interest rate and 12 interest periods, as they are altogether 12 annuity payments. Then we can treat this amount as a future value with respect to time 0 and change the annotations from P2 to F2. We can then multiply F2 with the single payment compound amount factor to shift the cash flows from the end of quarter 2 to time 0. In this factor, the interest period is 2. After we have calculated these 3 individual terms, we can sum them all up together to get the present equivalent value of these $20 billion, which is equals to $16.53 billion. And this is a pause and solve question. Erin just purchased a new sport car and wants to also set aside cash for future maintenance expenses. The car has a bumper-to-bumper warranty for the first 5 years. Irene estimates that she will need approximately $2,000 per year in maintenance expenses for years 6 to 10, at which time she will sell the vehicle. How much money should Irene deposit into an account today at 8% per year so that she will have sufficient funds in that account to cover her projected maintenance expenses? Okay, please try to solve these questions on your own, and we'll discuss these pause and solve questions during our class next week. Now we'll take a look at uniform gradient. Some problems involve cash flows that are projected to change, whether to increase or decrease by a constant amount each period. For example, because of leasing a certain type of equipment, maintenance and repair savings relative to purchasing the equipment may increase by a roughly constant amount each period. We can model these situations as a uniform gradient of cash flows. The table here shows such a gradient whereby a sequence of end-of-period cash flows increases by a constant amount G. The G is known as the uniform gradient amount. This is the cash flow diagram for uniform gradient increasing by G dollars per period. Note that the first uniform gradient cash flow, G, occurs at the end of period 2 rather than period 1. Bear in mind that all formulas related to the calculations of cash flow for uniform gradient is based on this assumption. It is easy to find the present value of a uniform gradient series. Similar to the other types of cash flows, there is a formula we can use to find the present value and a set of factors developed for the interest table. This is known as the gradient present worth factor, or gradient to present equivalent conversion factor. We can use this factor to find P given G, I, and N. Numerical values for this factor are given in column 8 of the interest table. We can also find A or S equivalent to a uniform gradient series. Okay, this is called the gradient uniform series factor. The numerical values of this factor is given by column 9 of the interest table. The factor for finding the future equivalent of a uniform gradient series can be derived as a function of the uniform series compound amount factor. The numerical values of this factor is not given in the interest table. If we wish to calculate the value of this factor, we have to use this formula together with the uniform series compound amount factor obtained from the table. The table here shows a uniform gradient series of cash flows. The annual equivalent of this series of cash flows can be found by considering an annuity portion of the cash flows and a gradient portion. In other words, we break the cash flows into end-of-year annuity and gradient. Here we get the annual equivalent formula as the summations of the annuity portions and the gradient portion. This is an example on using the gradient conversion factors to find the present value P and the annuity A. As an example of the straightforward use of the gradient conversion factors, suppose that certain end-of-year cash flows are expected to be $1,000 for the second year, $2,000 for the third year, and $3,000 for the fourth year, and that if interest is 15% per year, it is desired to find A. Present equivalent value at the beginning of the first year. B. Uniform annual equivalent values at the end of each of the 4 years. To solve this problem, as usual, we'll draw the cash flow diagram to visualize the cash flows. It is clear that this is an example of arithmetic gradient series, whereby the gradient amount is $1,000. The cash flow only started at the end of the second period, then continue up to 4 periods. The number of interest period end is therefore equals to 4, and the interest rate is 15%. To calculate the present equivalent, we can multiply the gradient amount, which is $1,000, with the gradient present worth factor at 15% interest rate and 4 periods. The value of the gradient present worth factor can be obtained directly from the interest table. Here the value of the factor is 3.7x6. Replacing this value into the equations, we will get the present equivalent P0 equals to $3,786. Now we look at question B. Calculate the annual equivalent value at the end of each of the 4 years. The annuity or annual equivalent can be drawn on the cash flow diagram like this. To calculate the annual equivalent, we can use this formula, whereby we multiply the gradient amount, which is $1,000, with the gradient uniform series factor at 15% interest rate and 4 interest period. The value of the factor from the interest table is 1.3263. This yields the annual equivalent of $1,326.30. Alternatively, we can use P0, which is the answer for question A, to calculate the annual equivalent. P0 can be multiplied with the uniform series capital recovery factor to obtain the same annual equivalent as you get above. And therefore, there could be multiple ways to calculate the equivalent. This is another example. Suppose that we are given cash flows from end of year 1 to year 4, which shows the increasing arithmetic gradient series, and we wish to calculate their present equivalent value at interest rate of 15% per year using the gradient conversion factors. We can draw a cash flow diagram like this. Observing the cash flow diagram, the gradient amount is actually $1,000. We cannot apply the gradient conversion factor alone to calculate the present equivalent, as the cash flow is actually a composite of an annuity series and a gradient series. This original cash flow diagram can be further broken down into two separate sets of cash flows, consisting of an annuity series of $5,000 plus an arithmetic gradient of $1,000 that fits the general gradient model for which the factors are tabulated. The summations of the present equivalence of these two separate sets of cash flows would equal the present equivalent of the original problem, which we are trying to find out. This is the formula to calculate the total present equivalent, as the summations of the present equivalent contributed by the annuity series and the present equivalent contributed by the arithmetic gradient series. The present equivalent of the annuity series is obtained by multiplying the annuity of $5,000 with 2.855, which corresponds to the uniform series present worth factor at 15% interest rate and 4 interest period. The present equivalent of the annuity series is equals to $14,275. The present equivalent of the gradient series, on the other hand, is obtained by multiplying the gradient amount of $1,000 with 3.786, which corresponds to the uniform gradient present worth factor at 15% interest rate and 4 interest period. The present equivalent of the gradient series is therefore equals to $3,786. The summations of both would give us a total present equivalent value of $18,061. Let's say you are now requested to calculate the annual equivalent of the cash flows. Again, this can be calculated as the summations of the annuity contributions from the annuity series and the annuity contributions from the gradient series. The annuity of the annuity series is just $5,000, whereas the annuity of the gradient series is $1,326.30. This is obtained by multiplying the gradient amount of $1,000 with the gradient uniform series factor at 15% interest rate and 4 periods, which is 1.3263. These summations give us the total annual equivalent of the cash flows equals to $6,326.30. Alternatively, we can calculate the total annual equivalent from the total present equivalent P0T obtained previously. We can multiply P0T with the uniform series present worth factor, which is 0.3503, to obtain $6,326.30. This value is exactly the same with the annual equivalent value you obtain using this formula. We will now take a look at another example, this time with decreasing arithmetic gradient series. Suppose that we have cash flows that are timed in exact reverse of the situations depicted in previous example, as shown in this table. Calculate the present equivalent at interest rate of 15% per year using arithmetic gradient interest factors. The cash flow diagram is given here. Similar to previous example, the original cash flow diagram can be broken into two separate sets of cash flows, consisting of an annuity series of $8,000 and an arithmetic gradient of $1,000 that fits the general gradient models for which the factors are tabulated. However, for this time around, the gradient series is subtracted from the annuity series, as the original cash flow diagram has decreasing cash flows. The formula here shows the total present equivalent of the cash flow is calculated by subtracting the present equivalent of the gradient series from the present equivalent of the annuity series. The present equivalent of the annuity series is obtained by multiplying the annuity of $8,000 with 2.855, which is the uniform series present worth factor at 15% interest rate and 4 interest period. The present equivalent of the annuity is given by $22,840. The present equivalent of the gradient series, on the other hand, is obtained by multiplying the gradient amount of $1,000 with 3.786, which is the uniform gradient present worth factor at 15% interest rate and 4 interest periods. The present equivalent of the gradient series is equals to $3,786. The subtractions here give us the total present equivalent value of $19,054. The annual equivalent of the original decreasing series of cash flows can be calculated by the same rationale. Here shows the total annual equivalent is obtained by subtracting the annual equivalent of the gradient series from the annuity of the annuity series, which is $8,000. The annual equivalent of the gradient series is $1,326.30. This is obtained by multiplying the gradient amount of $1,000 with the gradient uniform series factors at 15% interest rate and 4 periods, which is 1.3263. These subtractions give us the total annual equivalent of the decreasing series of cash flows equals to $6,673.70. We have just seen the uniform gradient of cash flows, but sometimes cash flows may change by a constant rate f cap each period, giving rise to a geometric gradient series. For example, a fixed amount of a commodity that inflates in price at a constant rate each year is a typical situation that can be modeled with a geometric sequence of cash flows. This table here shows a geometric gradient series. It begins at the end of year 1 and has a rate of growth f cap of 20%. This is the cash flow diagram for geometric sequence of payments increasing at a constant rate of f cap per period. We can see that the payments is increasing non-linearly with time, and the constant rate f cap is obtained from two adjacent annuities. We can find the present value of a geometric series by using the appropriate formula shown here. If the growth rate f cap is not equal to the interest rate I, we would use this formula to calculate the present value. The present value is equal to the initial cash flows in a series multiplied by 1 minus the product of the single payment present worth factor at I% interest rate and n interest period, and the single payment compound amount factors at f cap, growth rate, and n interest period. These are then divided by the difference between the interest rate and the growth rate. If the growth rate is equal to the interest rate, we will use this formula instead, which is the product of the initial cash flows in the series, the interest period, and the single payment present worth factor at I% interest rate and 1 compounding period or 1 interest period. Once we know the present equivalent or present value of a geometric gradient series, we can easily compute the equivalent annuity or future value using the previously seen basic interest factors. This is an example on the equivalence calculations for an increasing geometric gradient series. Consider the following end-of-year geometric sequence of cash flows and determine the present, annual, and future equivalent values. The rate of increase or the rate of growth is 20% per year after the first year, and the interest rate is 25% per year. In these equations, we can identify a few parameters, including the growth rate, F cap is 20%, the interest rate, I is 25%, the initial cash flows in the series is $1,000, and the number of interest period, N, is 4. Since the growth rate is not equal to the interest rate, we will make use of the first equations to calculate the present value. The equation is shown here. By substituting the values in the equations and finding the interest factors from the interest table, we can calculate the present values equals to $3,013 for this geometric gradient series. Since we have found the present value P, we can use P to calculate the annual equivalent and the future equivalent of the geometric series of cash flows. As usual, the annual equivalent can be found by multiplying the present value with the uniform series capital recovery factor to get $1,275.70. For the future equivalent, it is obtained by multiplying the present value with the single payment compound amount factor to get $7,355.94. Now suppose that the geometric gradient in previous example begins with $1,000 at end of year 1 and decreases by 20% per year after the first year. Determine the present, annual, and future equivalent under this condition. So in this case, the value of F cap is negative 20%. We can just replace F cap equals to negative 20% in the formula to calculate the present value while maintaining the values of the rest. We can find the value of this single payment present worth factor from the interest table, but not the value of this single payment compound amount factor with negative rate. This is because the interest table does not provide tabulations of factors for negative interest rate. Therefore, we use the equations to calculate the value of the factor instead. By working through the calculations, you will get the present value equals to $1,849.38. As in previous example, once the present value is known, we can use it to calculate the annual and future equivalent values using the correct interest factors. This is the pose and solve questions. Acme Miracle projects good things for their new weight loss pill, Losec. Revenues this year are expected to be $1.1 million, and Acme believes they will increase 15% per year for the next 5 years. What are the present value and equivalent annual amount for the anticipated revenues? Acme uses an interest rate of 20%. Here you are given a hint to solve the questions. Please try and we shall discuss next week. Up to this point, we have looked at examples where the interest rate is fixed throughout the entire analysis period. Interest rate could vary with time. When the interest rate varies with time, it is necessary to take the changes into account when determining the equivalent value. For example, these changes of interest rates can be observed in a variable rate mortgage. In this case, we often must resort to moving cash flow one period at a time, reflecting the interest rate for that single period. Let's now look at one example. Compounding with changing interest rates. Asher Smith is a 22-year-old senior who used the Stafford loan program to borrow $4,000 4 years ago, when the interest rate was 4.06% per year. $5,000 was borrowed 3 years ago at 3.42%. 2 years ago, she borrowed $6,000 at 5.23%, and last year, $7,000 was borrowed at 6.03% per year. Now she would like to consolidate her debt into a single 20-year loan with a 5% fixed annual interest rate. If Asia makes annual payments starting in 1 year to repay her total debt, what is the amount of each payment? Okay, here shows the cash flow diagram for this problem. This cash flow diagram illustrates that the four loans were borrowed from end of year -4 to year -1, and the annual repayment occurs over 20 years from year 1 to year 20 at 5% fixed interest rate. Before we can find the annual repayment amount, we need to find the equivalent value at time 0. This equivalent value is considered a future value, F0, with respect to the time when the loans were borrowed. To calculate F0, we can compound the amount owed at the beginning of each year by their interest rate that applies to each individual year. Okay, this is performed over 4 years until we get F0. For example, the future value at the end of year -3 is obtained by multiplying $4,000 with the single payment compound amount factor at interest rate of 4.06% and 1 interest period. And this value is added to $5,000 loan, which is borrowed in the same year. Okay, the value of this factor is calculated by using this formula. Okay, from these calculations, we get the future value at the end of year -3 equals to $9,162.40. Okay, this amount is brought forward to calculate the future value at the end of year -2. Okay, this value is multiplied with the single payment compound amount factor at interest rate of 3.42% and 1 interest period, and then added to $6,000 borrowed in the same year to yield $15,475.75. This process of compounding the amount is repeated until we get F0 equals to $24,689.22. Okay, now that we have the equivalent value at time 0 of the amount Asia borrowed, we can now treat this as a present value with respect to the annual repayment, and we can change the notations from F0 to P0. Okay, we can easily compute Asia's annual repayment amount by multiplying P0 with the Uniform Series Capital Recovery Factor at 5% interest rate and 20 interest period to get $1,980.08 per year. You may notice that in this problem, the total principal borrowed was $22,000, whereas the total interest repaid was $17,601.60. Okay, the interest amount is close to the amount of principal originally borrowed. Okay, the moral of this problem is that borrow as little as possible and repay as quickly as possible to reduce interest expenses. If we have interest rate that varies for each individual period, the present equivalent of a cash flow occurring at the end of period N can be computed with these equations, whereby IK is the interest rate for the K period. Okay, this part is actually the product of single payment compound amount factors for one interest period. Okay, the power 1 is omitted here. Okay, this is equivalent to multiply Fn with the product of single payment present worth factors, as both single payment compound amount factors and single payment present worth factors are inverse of each other. Okay, let's look at one example. If F4 is $2,500 and I1 is 8%, I2 is 10%, and I3 is 11%, then the present equivalent of the cash flow can be calculated by multiplying $2,500 with the product of single payment present worth factor at 8%, 10%, and 11% interest rates. all of which occurs within one interest period. Okay, this gives the present equivalent value of $1,896. Now we'll proceed to nominal and effective interest rates. More often than not, the time between successive compounding or the interest period is less than 1 year. For example, daily, monthly, and quarterly. It has become customary to quote interest rates on an annual basis, followed by the compounding period or interest period if different from 1 year in length. The annual rate is known as a nominal rate. A nominal rate of 12% compounded monthly means an interest of 1% would accrue each month, and the annual rate would be effectively somewhat greater than 12%. Let's take another example. If the interest rate is 6% per interest period, and the interest period is 6 months, it is customary to speak of this rate as 12% compounded semi-annually. A nominal rate is again 12% in this case. The more frequent the compounding, the greater the effective interest rate. In other words, the actual or the effective annual rate on the principal is not 12%, but something greater because compounding occurs twice during the year. The frequency at which a nominal interest rate is compounded each year can have a pronounced effect on the dollar amount of total interest earned. For instance, consider a principal amount of $1,000 to be invested for 3 years at a nominal rate of 12% compounded semi-annually. The interest earned during the first 6 months would be $1,000 multiplied by 12% divided by 2, as the interest rate is compounded semi-annually, and this gives the interest earned equals to $60. And then the total principal and the interest at the beginning of the second 6 months period would be that the principal plus the interest equals to $1,060. And the interest earned during the second 6 months would be $1,060 multiplied by 12% divided by 2 to get $63.60. Then the total interest earned during the year is 60 plus $63.6 equals to $123.6. Okay, finally, the effective annual interest rate for the entire year is equals to $123.6 divided by the principal of $1,000 times 100 is equals to 12.36%. So the effective annual interest rate is actually higher when the nominal rate of 12% is compounded semi-annually. The effect of more frequent compounding can be easily determined. Let R be the nominal annual interest rate and M the number of compounding periods per year. We can find I, the effective interest, by using this formula, whereby I is equals to 1 plus R divided by M, and the entire content here is raised to the power of M minus 1. The actual or exact rate of interest earned on the principal during 1 year is known as the effective rate. It should be noted that the effective interest rates are always expressed on an annual basis unless specifically stated otherwise. In engineering economy studies in which compounding is annual, I would be equals to R. The effective rate of interest is useful for describing the compounding effect of interest earned on interest during 1 year. Here are 2 examples on how we can find the effective interest rates. For an 18% nominal rate compounded quarterly, the effective interest is given by this formula, whereby R would be 0.18, corresponds to nominal rate of 18%, and M is 4 as the nominal rate is compounded quarterly, which means 4 times in a year. Okay, this gives the effective interest rate of 19.25%. For a 7% nominal rate compounded monthly, the effective interest is given by this formula whereby R is 0.07 corresponds to 7% nominal rate, and M is 12 as the nominal rate is compounded monthly, which means 12 times in a year. Okay, this gives the effective interest rate of 7.23%. Figure here shows the cumulative amount of interest earned while $1,000 is compounded at a semi-annual frequency. We can observe that the cumulative amount of interest earned is increasing non-linearly with time. This is due to the compounding effect of interest earned on interest. This plot shows the cumulative amount of interest earned over 3 years result from monthly compounding. As compared to the previous plot, the effective interest rate is higher although the same principal amount is compounded. This plot shows us that the more frequent the compounding, the greater the effective interest rate. The table here tabulates the effective interest rate for various nominal rates and compounding frequency. What we can conclude from this table is that the more frequent the compounding, the greater the effective interest rate. This is an example on the effective annual interest rate. A credit card company charges an interest rate of 1.375% per month on the unpaid balance of all accounts. The annual interest rate they claim is 16.5%, which is given by multiplying the interest rate with the number of compounding period in a year, which is 12 months. So what is the effective rate of interest per year being charged by the company? Okay, the effective rate of interest can be calculated using this formula. So R here is the nominal rate, which is 16.5%, and M is the number of compounding period, which is 12 compounding periods in a year. Okay, this gives the effective interest rate of 17.81% per year. Okay, the nominal interest rate is also known as the annual percentage rate. In general, it is true that the nominal interest rate is given by this formula, whereby R divided by M is the interest rate per period. We can use the effective interest formula to derive the interest factor. As the number of compounding periods M gets larger, we find that the effective interest formula can be turned into this form, which is exponential of nominal interest rate R minus 1. For single amounts with interest that is compounded more than once per year, and under the conditions that we are given the nominal interest rate, the number of compounding periods per year, and the number of years the analysis to be performed, then we can use these two equations to calculate the future annual or present equivalent values. One example will be shown next. For uniform series and gradient series with interest that is compounded more than once per year, the formulas and tables for uniform series and gradient series can be used. We'll also look at 3 examples of this kind of cash flows. This is the example on finding future equivalent when the interest is compounded quarterly. Suppose that a $100 lump sum amount is invested for 10 years at a nominal interest rate of 6% compounded quarterly. How much is it worth at the end of the 10th year? We can identify a few variables from these equations, including the present value, which is $100. The nominal interest rate is 6% compounded quarterly, which means there are 4 compounding periods per year. This leads to a total of 40 interest periods over the length of 10 years. The interest rate per interest period is 1.5%. which is given by dividing the nominal interest rate with 4 compounding periods per year. And with these informations, we can calculate the future equivalent directly using these equations. The future equivalent is equals to the present value multiplied by the single payment compound amount factor with 1.5% interest rate per period and 40 interest period. This gives a value of $181.40. Alternatively, we can calculate the effective interest rate before using it to find the future equivalent. The effective interest rate is given by this formula, which is 6.14% per year. We can plug this into this formula to calculate the future equivalent. Since the effective interest rate is an annual rate, the interest period therefore should be based on year rather than month. So here we have 10 interest period to be used for the calculations of the interest factor. This yields a future equivalent of $181.40, which is exactly the same as the answer given by the calculations above. This is an example on the calculations of annuity when the interest rate is compounded more than once per year. Computing a monthly auto payment. Stamp Moneymaker has a bank loan for $10,000 to pay for his new truck. This loan is to be repaid in equal end-of-month installments for 5 years with a nominal interest rate of 12% compounded monthly. What is the amount of each payment? Again, we can identify a few variables from these equations. The present value is $10,000 and the nominal interest rate is 12%. Compounded monthly means there are 12 compounding periods per year. Therefore, there are 60 installment payments given by multiplying 5 years with 12 months per year. The interest rate per month is 1% given by dividing the nominal interest rate by 12 months. Plug in these values into this formula, you will get the annuity payments equals to $222. Notice that there is a cash flow at the end of each month of the interest period, including month 60 in this example. This example is about uniform gradient series and semi-annual compounding. Certain operating savings are expected to be zero at the end of the first 6 months, to be $1,000 at the end of the second 6 months, and to increase by $1,000 at the end of each 6 month period thereafter, for a total of 4 years. It is desired to find the equivalent uniform amount A at the end of each of the 8 6-month periods if the nominal interest rate is 20% compounded semi-annually. Here we can identify a few variables from these equations. The gradient amount is $1,000 and the nominal interest rate is 20% compounded semi-annually, which means there are 2 compounding periods per year. Here shows the cash flow diagrams, and from these informations we can identify the interest rate per period equals to 10%, which is given by dividing the nominal interest rate of 20% by the number of compounding period, which is 2. The number of interest period would be 8, with the length of each period equals to 6 months. The cash flow diagram here shows that we need to identify the annuity of this gradient series, and both cash flow diagrams are equivalent. The annuity is given by multiplying the gradient amount of $1,000 with the gradient uniform series factors at 10% interest rate and 8 interest periods, which is equals to $3,004.5. This is an example on finding the interest rate on a loan. A loan of $15,000 requires monthly payments of $477 over a 36-month period of time. These payments include both principal and interest. You are required to answer several questions including A. What is the nominal interest rate for this loan? B. What is the effective interest rate per year? And C. Determine the amount of unpaid loan principal after 20 months. To answer question A, we can set up an equivalence relationship like this to solve for the unknown interest rate since we know that the present value is $15,000, the annuity is $477, and the number of interest period is 36 months. Here, the annuity is equals to the multiplications of the present value with this uniform series capital recovery factor at monthly interest rate of IMO and 36 months interest periods. We can simplify these equations and get the interest factors equals to 0.0318. We can now look through the column on the uniform series capital recovery factor in the interest table to find the values of I close to 0.0318. Okay, from the table with the interest rate equals to 0.75%, we can find the exact factor value. Okay, therefore, we can conclude that the monthly interest rate IMO is equals to 0.75%. To calculate the nominal interest rate, we can multiply the monthly interest rate with 12 months to get 9% per year, compounded monthly. To answer question B, we can use this formula to calculate the effective interest rate per year, which is equals to 9.38% per year. To answer question C, we can find the amount of the unpaid loan principal after 20 months by finding the equivalent value of the remaining 16 monthly payments as of month 20. Here, the present equivalent value at month 20 is equals to the annuity multiplied with the uniform series preservoir factor at 0.75% of interest rate and 16 interest periods to yield $7,166.59. So you can see that after 20 payments have been made, almost half of the original principal amounts remain. And notice that we use the monthly interest rate of 0.75% in the calculations since the cash flows are occurring monthly. Now we'll proceed to interest formulas for continuous compounding and discrete cash flows. In most business transactions and economy studies, interest is typically compounded at the end of discrete periods. As has been discussed previously, cash flows are assumed to occur in discrete amounts at the end of such periods. However, in most companies, cash is flowing in and out in an almost continuous stream and should be immediately put to use. We can allow compounding to occur continuously throughout the period. Actually, the effect of this compared to discrete compounding is small in most cases. Here is the list of continuous compounding interest factors that you could put to use. And other factors can be derived from these factors. The applications of these factors are similar to those for discrete compounding, except that their formulas are different, and we should refer to the interest table for continuous compounding for the values of the different factors. I have uploaded the table for your reference in Spectrum with this name. Here again shows the complete list of continuous compounding interest factors that you could put to use. R underscore is used to represent nominal annual interest rate compounded continuously. This example shows continuous compounding and single amount. You have $10,000 to invest for 2 years. Your bank offers 5% interest compounded continuously for funds in a money market account. Assuming no additional deposits or withdrawals, how much money will be in the account in the end of 2 years? So here you are requested to calculate the future equivalent of the account after 2 years. Okay, here is the solution. Okay, you can use this formula to calculate the amount of money in 2 years' time. So the future equivalent is equal to the present value multiplied with single payment compound amount factor with the continuous compounding interest rate of 5% for 2 years. Okay, this value of the factor here can be evaluated using this formula. Okay, this gives the future equivalent value of $11,052. If the interest rate was 5% compounded annually, the account would have been worth $11,025. Okay, you can see that the difference between discrete and continuous compounding is actually quite small. Now let's take a look at continuous compounding and annual payments. Suppose that one has a present loan of $1,000 and desires to determine what equivalent uniform end-of-year payments A could be obtained from it for 10 years if the nominal interest rate is 20% compounded continuously and the end is infinity. Okay, here shows the solutions. We can make use of these equations to calculate the annual payments. Okay, since the capital recovery factor is not tabled for continuous compounding, we can substitute this with X inverse, which is the present worth factor. Okay, this present worth factor is tabulated in this table for continuous compounding, and the value is equal to 3.9054. So you substitute this into the equations and to get the annual payments of $256. And note that the answer to the same problem with discrete annual compounding, whereby m is equals to 1 is equals to $239. Okay, again, you can see that the difference between discrete compounding and continuous compounding is actually quite small. This is the last example, which is on continuous compounding and semi-annual payments. An individual needs $12,000 immediately as a down payment on a new home. Suppose that he can borrow this money from his insurance company. He must repay the loan in equal payments every 6 months over the next 8 years. The nominal interest rate being charged is 7% compounded continuously. What is the amount of each payment? So here shows the solutions. And the nominal interest rate per 6 months is 3.5%, which is obtained by dividing 7% by 2. The number of interest period is 8 years times 2 6 months period equals to 16. Thus, the annuity for each 6 months is given by this formula. Annuity is equals to the present value of $12,000 multiplied with the uniform series capital recovery factor, which is equivalent to the inverse of the uniform series present worth factor. Okay, by substituting terms in these equations, we can find the factor values equals to 12.038. Okay, with this value, we can determine the value of the annuity per 6 months to be $997. Okay, this is the end of this topic. Okay, thanks for listening. And I have prepared some tutorial questions for you. Please go through and we shall discuss next week. Okay, see you again. Bye bye.